I'd first like to extend my gratitude to the Alakija family, to Ade, my friend, and to the children, Alero, Tony, and Sheyi. Thank you very much for asking me to give this inaugural lecture in memory of your mother, who I knew, and I met her on a couple of occasions. I wonder if you can hear me at the back. Yes. So it's a great honor for me to be here and to talk about a subject that I think would have excited your mother for a number of reasons which I will try and allude to during the talk. The Abayomis are no strangers to the Alakijas, and so I feel that I'm in the right place today to give this very important first memorial lecture of the DFAF. I'm also here with some of my family, my daughters and my friends. So my daughter asked me this morning, what is genomics? So I said, well, I'll try and explain it as best I can. But genomics indeed is a very complex subject. And if by any chance you understand anything I've said at the end of the talk, then I would have achieved my mission. But suffice to say that even geneticists don't understand genomics. And, we keep getting surprised on a daily basis by some of the things that we discover around the subject of genomics. So thank you very much to the Master of Ceremony, Yinka Akikugbe, for your very generous introduction. As he said, I've known him since we were children, and I first encountered him in a very intimate way in King's College, where I believe that Yinka was one of the people that was responsible for me not getting expelled from King's College, because he was 2 years ahead of me, and he kept calming me down and saying, no, you have to carry water, and you have to address your seniors and say, please. And I said, why should I do that? He said, if you don't do that, you're going to get into a lot of trouble. And I did get into a lot of trouble. But after about 6 months of coaching, I settled down and found myself in the right place at the right time in King's College. What Yinka didn't tell you is that he's an avid polo player. And we used to play polo together under the great mentorship of Amadou Yakubu, who was one of Africa's greatest polo players. And I remember on many occasions playing on opposite sides against Yinka and thoroughly thrashing his team. So that is my claim to fame. So just a little bit of background about who I am. I started my education in Maryhill in Ibadan, convent school. And then I went to King's College, and then I went to Loyola College, and then I went to International School, University of Ibadan. And then I ended up in the University of London, where I did my medical degree. And I'm currently associated with the following institutions. I'm at the Nigerian Institute of Medical Research, Lagos State. We're going to talk today about a number of topics around genomics. I'm going to talk about genomics being the code of life. I'm going to talk about the enigma of genomics, a topic we call the central dogma, and I hope that I'll be able to explain that to you. We're going to talk about a little bit about evolution, and then we're going to talk about some of the applications of genomics as we know them now in terms of gene editing, gene drives, and some of the biosecurity threats. And then we're going to talk about the genomic age and its implications for Africa and Nigeria. So 40 or 50 years ago, it was quite easy to get onto the biotechnology train. It was a slow-moving train, and you could literally jump on it like these guys are jumping on this train without harming yourself. Next slide. But today, the genomic train is moving at supersonic speed. And it only stops at a few stations. And we'll talk a little bit about that. You cannot jump on this train. You will kill yourself. You have to wait for the train to stop and be let onto the train. So we're going to try and find out what we must do to allow ourselves to get onto this train. Next slide. So the world is moving in the realm of what we call big science. And big science is characterized by large international trans-border consortia, cooperation between Japan, the United States, Europe, China, South America, lots of money. They're collectively accelerating knowledge through discovery. It operates at a very fast pace. And one of its first projects was the Human Genome Project. And since the Human Genome Project, we've discovered so much about the code of life. So what is human life? And how does this miraculous body that we walk in function? I'm going to try and give you the simple version first. At conception, there's a fusion of gametes, and that's the ovum and the sperm, and each of them have half of your genomic complement, just half each. So when they get together, they form a complete complement of your genes, and that's what it looks like under the microscope. And when we rearrange them, we can put them in order, and you have one chromosome from each parent. And if you're lucky enough to have a double X, you will turn out to be female. And if you're unlucky to have a short Y, then you're short of genes, and that makes you into male. And there are many reasons why we perform the way we perform. So each one of you has a unique genomic profile. And it's like your fingerprints. There are no two people alike. Even identical twins have some genetic variation. So the genetic structure I've described to you, 23 pairs, and you have one chromosome from each parent, and those chromosomes are made up of DNA, which is a nucleic acid. And the nucleic acid is what contains the code of life. And these are the chromosomes, and if we take one of them and we unwind it, then inside the chromosome you will see these colored chemicals, and they are what make up the code that you have inherited that determines who you will become. The chromosomes are responsible for producing your proteins, and your proteins form your organs, and your organs constitute together to form your living being. You can change. So there goes your DNA, and eventually your nucleic acid, which resides in your genes, forms your proteins. Next slide. And at conception, you start to develop. One cell divides into 2 cells, and 2 cells divides into 4 cells, and so on exponentially. Next slide. And you form the embryo. And the embryo eventually develops in the uterus until it is fully matured. Next slide. And voila, we give birth to a beautiful bouncing baby. Next slide. Now, there are a number of enigmas. The first enigma I'm going to talk about is cell differentiation. Next slide. One of the greatest mysteries in biology is how a complex human being can be derived from a single cell. So in the center is the embryo. And as the fetus is developing, it starts to form different organs: red cells, muscles, fat, heart, brain. How does this happen from just one single cell? That is, till today, a great mystery. And as you develop, you form this very complex entity: a brain, a skeletal structure, all your organs, all the nervous systems, your blood supply. Next slide. And you can see from this diagram how complicated the entity of who you are, how complicated it is, and how all these structures work together to form the entity of a human being. Next slide. And that human being is capable of very complex physical and mental activities. Next slide. Now, enigma 2. Where are we from and where are we going as a race? In other words, where did the human race derive from? The classical theory is the theory of evolution, where we evolved from a more primitive living creatures to human Homo sapiens as we are known today. Next slide. And the evolution or the Darwinist theorists believe that we evolved out of creatures that were in the sea, that emerged onto land, and eventually created the primates, and we developed from the primates. So that's the evolution theory. Now, mathematicians have worked out that the probability of a molecule arising by chance in the bottom of the sea is almost an impossible probability, 10 to the power of 164. I can't tell you what that means, but that's in the gazillions. So the evolutionists, I think, are beginning to lose ground, because apart from the almost impossible probability, when you think about the evolution theory, we're missing certain things. And we're missing the links between the animal entities that we see on Earth. So there is no halfway between a monkey and a human being that we know of. So there is a big debate between the creationists and the Darwinists. And we believe that random evolution is getting weaker and weaker because it can't explain the very complexity of life as we know it. Back. And so the creationists have got the upper hand at the moment. The real debate actually now is between the creationists and the simulationists. So both of them are creationists, but one believes that there is a God that created life, and the mathematicians, who are also creationists, believe that we are all living in a simulation. So it depends where you're coming from. This is part of the spiritual creationist movement, a living God that decided to create man in the Garden of Eden. Next slide. And man was formed from the earth. And the complexity of biology and genetics as we know it supports this kind of ideology. Next slide. The simulationists, though, believe that life is one big hologram, controlled by a creator, but a mathematical creator, and that life is a mathematical simulation. And there's lots of evidence for this as well. And as we improve in our speed of computational creation and analysis, we're able to create simulations and holograms. And these are holograms. These are not real. Some of you, my daughters took me to a concert in Cape Town. Was it Justin Bieber? And it was very loud. And my whole body was shaking and vibrating. But I was amazed at the holographic creation of Justin Bieber. There was Justin Bieber, but there was a hologram as well. So simulation is not so far-fetched. Next slide. And some people believe that there is a simulation controller somewhere in the outer universe. Next slide. And that we can simulate nature almost to perfection. Next slide. And this is an idea. Some of us who are forced to go and watch movies with our children, a lot of the movies that we see are all simulations. Next slide. Now, some of you may have heard of quantum physics. And the difference between quantum physics and natural physics is very simple. If I jump off this podium, then Newton's law will kick in, and I will drop to the ground and probably break something. Quantum physics is subatomic physics, and the laws of quantum physics are totally different from the laws of natural physics. And I'm just putting on this screen the slide called quantum entanglement. And basically, what quantum entanglement means is that if two molecules arise from the same origin, so for example, if I take a molecule from myself and I move it to Mars, whatever is happening to me here will be happening to my same molecule on the planet Mars. So whatever I do to myself, the same reaction will happen. It doesn't matter where that other molecule is. Now, this is a little bit of a mystery. It has been proven over and over again, and nobody can explain quantum entanglement. Why do I bring this up? Because we're moving into the era of quantum computing. And quantum computing is going to take humanity to a level that we cannot imagine. And a quantum computer, there are a couple of quantum computers at the moment. They belong in very high security facilities around the world. And quantum computers have exponentially higher computational analysis than the computers that you use every day. That means we're going to start to be able to understand very complex laws and physics of life very soon. And these quantum computers can either work greatly in our interest, or they can become major problems for us, depending on how we use them. And it is believed that when quantum computers become part of our everyday life, then we're going to be moving more and more into the era of simulation and some of the fantastic, far-fetched space-age technology that we normally see in the movies. Next slide. Now, when you combine genomics and quantum physics, we're moving into an era that we call augmentation. And what is augmentation? I'll come to it a bit later. But essentially, you can see where man is going. Man is going into the era of augmentation, where a human being, his very physical being, will be augmented by computers or by genomics to be almost, well, not almost. Some of you will remember a show called The Bionic Man. It used to be so amazing then, but now we are moving into the era of bionic human beings, where you'll be able to see like an eagle, you'll be able to hear subsonic sounds, you'll be able to carry out computational analysis with your brains, and that's what we're talking about, the augmented human being. And this is not science fiction, this is happening as we speak. Next slide. Now, Enigma 3. Everything that happens to you in life is primarily controlled by your genes. That is called the central dogma. So those genes that I showed you earlier on control your every life. Everything about you, how you develop, how you grow, how you think, how you relate, is controlled by your genes. But the question that we've had for a long time is, well, if your genes control who you are, who controls the genes? Who tells the genes what to do? And that's the central dogma. Next slide. And it is responsible for growth, maturation, skills that you acquire, and of course the aging process. Next slide. And that is the same dogma. Your genes is converted to another nucleic acid, to your proteins, and you evolve out of that. Next slide. Now there's a fundamental problem with the central dogma, because we cannot understand who controls the genes. You can't have something autonomous. Something has to control something. So we are stuck with this central dogma, with 6 billion bases that forms your genetic code, which forms your 80,000 proteins per cell, which creates you as a human being. There is a problem with the central dogma. Next slide. And this is just a cartoon showing how the genes are converted, are opened up, your code is exposed, and your body reads the codes, and you form proteins which forms your organs. Next slide. So let's talk about the fourth enigma. Africa, the cradle of humanity. Next slide. So Africa is made up of 3,000 ethnic groups. And one day I was giving a talk and somebody corrected me and said they're not ethnic groups, they're ethnic nations. So for example, the Yoruba are an ethnic nation, the Hausa are an ethnic nation, the Bini are an ethnic nation. And you can see the complexity of Africa. There is no part of the world as complex as Africa in terms of ethnic, human, genomic diversity. Next slide. And it is believed that humanity, as we know it all over the world, arose from the heart of Africa. That all of humanity resided in Africa, and over thousands of years, several Eves and Adams emerged out of Africa to populate the rest of the world. Next slide. So it is said that black woman is the only living creature whose DNA has, it's raining, whose DNA has the footprint of every woman on earth. So inside black woman resides every woman around the world. And if you can see, the children of black women of Africa can give birth to children that resemble the diversity of humanity as we know it on earth. Next slide. So if you take the whole of Africa and you put them through a genomic machine to separate them, next slide, you will see that if we took this population and separated you genetically, we would find this huge diversity of human beings that reside in Africa. Next slide. And these people have migrated out of Africa and spread their genomic code all over the world. Next slide. The problem is, the richness of that diversity remains in Africa. Those that left Africa, the range of diversity is very narrow, as you can see from the either blue or white dots. But when you come to Africa, you have, I can't display it on this slide, but there are thousands and thousands of genetic variations in Africa, and very few genetic variations outside of Africa. Next slide. So when you look at the diversity of humanity from around the world, they all originated in one form or the other from the continent of Africa. Next slide. So there is a new scramble for Africa. We know about slave trade, we know about colonialism. So what's the neo-colonial scramble for Africa? Because science needs to understand who you are as human beings. The only way you can understand who we are as human beings is to go to the origin. And the origin is in Africa. And therefore, the world wants the complete human ethnic biodiversity that resides in Africa for it to understand who we are as human beings. Next slide. And that understanding translates into billions of dollars. And what we're doing on the continent of Africa is we're actually giving away our bioresources free of charge, like we've done for centuries. And we've got to wake up. Your biological diversity is so rich, and it is in such demand. And the Commissioner of Health for Lagos State is here. He understands that this rush for African human biological diversity is so aggressive, and it is coming in every form and fashion, and we need to be aware of it and to protect our biological diversity. Next slide. So let's try and understand these enigmas that I have just alluded to. The Human Genome Project was one of the first multi-international consortiums of researchers, high-powered researchers that came together with a lot of money to try and unravel the human genetic code. It was called the Human Genome Project. Next slide. It started in October 1990. Next slide. And after 12 years and $3.8 billion, the human genetic code was cracked. 12 years. In those days, we had slower computational machines, so it took a lot of time. Next slide. And it ended in April 2003. Next slide. This is the kind of laboratory, thousands and thousands of what we call sequencers were used to unpack the genomes and to try and understand what makes you a human being based on your genomic code. Next slide. It is interesting, and I alluded to this just now. The United States, Europe, and Japan and China put $3.8 billion into the Human Genome Project. That's a lot of money. But what did they derive? They derived $800 billion from that $4 billion investment. That's almost 200, mathematicians here, that's 2,000% interest. That just gives you an idea the value of biological resources. So if you were going to put 4 naira into a bank, and some years later you come back and collect 800 naira, you say, wow, that is fantastic business. And the bioeconomy is indeed fantastic business. Next slide. But from the Human Genome Project, we discovered some shocking truths. Next slide. Genetic Trivia 1. Every cell contains 2 meters of nucleic acid or genetic material. If you unpack the genetic material from every cell in one human being, next slide, you can go to the moon and back 6,000 times. That just shows you how each human being, how much information is in a single human being. Now you can start to understand why the creationists are gaining ground over the evolutionists, because this is just too fantastic to have come about by random selection. Next slide. The next genetic trivia, which shocked us, was that only 2% of your genetic material actually codes for genes. And we discovered that we only have 30,000 genes. We thought we had over 100,000 genes, but the Genome Project proved that we only have 30,000 genes, which is a bit of a shock to us. But even more shocking was the fact that only 2% of your genetic material actually codes for genes. Next slide. Therefore, most of your genetic material is not coding. Next slide. So what is that 98% of your genetic material doing? Well, we've discovered a little bit about what it does. It's responsible for regulating the genes that do code. But we've discovered that human beings are different from other creatures on Earth. And some of the differences that we have is that we can do complex computational analysis. We have consciousness. We have links to other dimensions. And we have spiritual antennas. And so it is likely that 98% that we don't understand is what separates us from the rest of life. So if you think about your genes that are working, you actually need an orchestra maestro to coordinate how those genes actually function. But this diagram is actually wrong because you have more control genes than you actually have genes. Next slide. So the adage that too many chefs spoil the broth is not actually right when it comes to genetics, because you need many chefs to create who you are as a human being. Next slide. The next trivia we discovered is that human beings have only twice as many genes as a fly. Next slide. And trivia 4, 10% of our genes we share with our ecosystem. Next slide. And that gives us the idea that there is a concept of original spare parts. It's just like when you take your car to the mechanic, sometimes they can use a spare part that comes from another type of vehicle because all vehicles are using certain spare parts that are identical. So it proves that we are actually part of the ecosystem because we share genes with our ecosystem and our partners in our environment. Next slide. So the concept of One Health, you may have heard about One Health. One Health says that our health depends on the health of our environment. But if we live in an unhealthy environment, we get sick. But what people don't often say is that if we live in a healthy environment, we actually do better. So it cuts both ways. So the One Health paradigm is not just about we don't want to get sick from sick animals or sick plants, but actually if we injure our ecosystem, we're actually injuring ourselves because we derive a lot of benefit from the environment. And therefore, when we think of ourselves as being the pinnacle of the ecosystem, we're actually wrong. We are part of the ecosystem, and we must protect our environment if we as human beings want to live a healthy life. Next slide. Let's try and understand differentiation and the central dogma. Where is the control? We've just explained that people think that the genes are your control. Next slide. So if you look at the chromosomes, think of them as a keyboard. Next slide. The great Stevie Wonder has a keyboard. He has many keyboards. He's surrounded by keyboards. Have you ever gone to a concert where the keyboards are playing themselves? No. The artists play the instruments. So if your genes are the keyboards, something has to play the genes. Next slide. So we've discovered that by putting cells inside dishes and surrounding them with things that we believe will tell them what to do. We tell this cell, make yourself into a muscle. It will just sit there and it will do nothing. But if we put the right environment in that test tube, it will start to make muscle, or it will start to make a brain, or it will start to make a kidney. Next slide. So, it depends what surrounds the cell. And that substance goes into the cell, down to the genes, and starts to give it instructions of what to do. So your cells can do nothing on their own. They need to be instructed. And they are instructed by who? They are instructed by you. Next slide. What you are thinking translates into chemistry. And that chemistry goes into your blood. Next slide. So if you think positive things, you'll get positive chemicals. If you think negative things, you'll get negative chemicals. Next slide. And so apart from what you think, what you surround yourself with instructs your cells. So if you do exercise, you get a signal that goes to your cells that is based on the exercise signal. If your environment is clean, it sends a signal to your cells. If your environment is polluted, a different signal goes to your genes. If your emotional health is sound, you're thinking positively, you're thinking about good things, is different, your chemistry is different from if you're constantly thinking about how to steal money and how to do wickedness. And that translates to your genes and your diet. And everything in your environment is translated into chemical signals that instructs your genes. Next slide. So what you're thinking forms chemicals. Your thoughts are chemical reactions. And that's your brain. And that chemical reaction is transmitted into the bloodstream and through your nervous system to every cell in your body. You've heard about the fright and flight. If suddenly there's an explosion there, everybody is going to jump up, and suddenly there's a rush of fight and flight chemicals in your body, and your body kicks in and you fly out through. You can even jump over that barrier, which you can't normally do if you didn't have the flight and flight mechanism in place. Next slide. So those chemicals float in the blood and they enter the cell and they go to the genes and they instruct the genes what to do. Next slide. And this is a bit complex, but it's very simple. There are receptors on the surface of your cell, and your brain chemistry goes into your bloodstream, and your bloodstream goes to the cells, and the chemical instructions go into your cell and into your nucleus and to the genetic material, and that is what instructs your body on what to do, how to grow, how to react, how to stay well, or how to get sick. Next slide. Now, the magic of pregnancy is one of the great mysteries to us as human beings. The fetal development, especially in the early stages, is dependent on the mother's hormones. So the mother's chemicals, when a woman is pregnant, her whole chemistry changes. And that chemistry is changing because it has to instruct the development of the evolution of a new human being. And that human being resides in the womb. You cannot grow a fetus outside of a mother. It's not possible because the fetus depends for instruction from the mother. Next slide. And so early life stresses change the way children develop and what will happen to you in future. Next slide. So if you subject a child to early life stress, like I was subjected to stress in King's College, it has long-term effects on you. And 20, 40, 30, 50 years down the line, you manifest with some negative physical attributes. So it's very important that the developing child in the womb and the developing child through kindergarten and nursery and the early childhood learning, and that's for the doctors that are into early childhood learning, that the environment of a child is protected because you'll be sending signals to the DNA of the child, which is going to set up that child for diseases down the line. This is proven fact, and this is reality. Next slide. Now, we've been talking about genomics. As if genomics is not complicated enough, there's a new concept called epigenomics. Everyone thought that there's evolution, but we now know that genetic fidelity is extremely strict. You cannot walk around changing your genome codes. If you do, you will end up with cancers and all kinds of funny diseases. So the body makes sure that your genes are exercise extreme fidelity. So from one generation to another generation, your genes more or less remain the same. They do change, but very, very, very slowly. And if you change one of those codes, and those codes are not beneficial, then the body will shut down that cell and instruct it to commit suicide. But epigenetics is extremely dynamic, and I'll explain it to you in a second as best I can. The term epigenetics refers to inherited changes in gene expression that does not normally involve changing the genetic code. In other words, what you are exposed to in your environment will create an epigenetic change at your genetic level. The genes do not change, but how you express those genes is called epigenetics. Next slide. And you can either turn your genes on or you can turn them off. And this is just a schema of how that works. Next slide. So, around all your genes is a switch. And there are thousands of genes. And there's thousands of regulators. And around each gene and each regulator are these on and off switches. And epigenetics is where those switches are switched on or off, depending on your exposure in life. Next slide. So what happens is on your genes, these red dots are either your switch is on or your switch is off. If your switch is on, it means your body can read that gene. If the switch is off, you cannot read it. And depending on what you do in life, your genes will be switched on or off. For example, a pregnant mother has a baby and is smoking. The effects of that smoking will affect the mother. Her genes will be switched on or off. Mostly bad genes will be switched on and good genes will be switched off. That's the effect of smoking. the fetus will also be affected. Bad genes will be switched on and good genes will be switched off. But here's the catch. The gonads of the baby, in other words, if that's a female child, the tissue that's going to form the ovary, which is how that child is going to give birth to her children, those genes are also affected. And it is inherited. So epigenetics is actually the way in which we translate our environment through our genes from generation to generation. We don't actually change the genes, we change how the genes are expressed. Now, it doesn't just apply to bad things, it applies to good things. It constantly amazes me how the next generation, the young generation, they can be as young as 2 or 3 years old, and you give them a cell phone, and they know how to use it. It baffled me for years, how the next generation are so computer literate. Well, guess what? It's inherited. You are computer literate. You switch on your computer literate genes. You have a child, and those genes are switched on in the child. So a child comes to Earth already programmed for computational analysis. That's just an example of how we can transmit good things and bad things to the next generation almost like that. And that's called epigenetics. So epigenetics is very powerful, and our environment is determined by what you transmit from one generation to another. Next slide. So what is the future? Slide. We're moving into the era of personalized medicine. That video that we saw of the foundation going to a downtrodden environment, I don't know what jumped out at you, but what jumped out at me was the complete disregard for the environment, the pollution, the dead water, the infections in the environment. Those kids that grow up in that environment, their antibodies are superhuman. If I go into that environment and drink water from what those kids normally drink for, I'm sure I'll be admitted to intensive care. But we've got to do something about our environment. Gene editing, cryotherapy, transhumanism, computational physics, and computational power. Next slide. So in medicine, because we are at a medical arena, our diagnostics capacity are changing because of genomics. Our treatment is getting smarter and intelligent. Doctors are becoming what we call signal pathways engineers, and I'll explain that. And the public are demanding personalized medicine. What is personalized medicine? I'll explain it. People will preemptively be able to choose prolonged life. And they say that in a couple of decades from now, you will have an option to live or to die. In other words, you can carry on living for as long as you want. That is where genomic medicine is going. Now, when you give a sample to a genetic engineer and they give you the results, you can't understand it. It has to be interpreted to transmit the information that your doctors will use to manage you, either as a sick person or as a well person, because well people are going to doctors now to determine what conditions they're going to develop in the future. And that's what genetics can tell you. What diseases do you predispose to in 5, 10, 20 years? Do you want to know? And if you want to know, then you can do something about it. Next slide. So this is the cycle. By understanding your genes, we can understand the biology of your genes. We can understand the biology of disease. We can advance the science of medicine, and we can treat you with very advanced technology. Next slide. So if you have a cancer, we'll take the cancer, we'll unpack the genes of the cancer, we'll look at which genes are switched on and which genes are switched off, and what is driving the cancer. And then we can go into the cell and we can switch the genes around. So the era of cancer treatment being one where we give you all these poisonous drugs and your hair falls out and you vomit and your skin almost falls off and you lose weight and you look terrible, that era is moving out. And what is moving in is personalized medicine, where we understand the drivers of cancer through those switches, and we have chemicals now or compounds that can go into the cells, switch those genes back to normal, and push the cancerous cells back to normal cells. So that is the era that we're working on now, and that's not, again, futuristic. This is medicine as we're practicing in advanced communities. Next slide. We'll be able to take blood rather than go to the organ. Let's say you have a cancer in your liver. Instead of doing that dangerous procedure of trying to biopsy the liver, we'll just take a sample from your blood, and those cancerous cells will be in the blood, and we'll be able to work out what the problem is. Next slide. Now, if you have a condition, let's just say colon cancer. All those people up there have colon cancer. You go to the doctor and they give you standard colon cancer treatment. They poison you, your hair falls out, your gut falls to pieces, you feel terrible. At the end of the day, 3 out of you get better, 3 have no effect, and actually some of you do worse. So something is wrong with that green pill. That green pill is not for everybody. Next slide. Next slide. Keep going. Keep going. Next slide. Basically, all this is saying, next slide, is that there is a different pill for everybody. And we as genetic engineers and genetic practitioners need to find out, based on your genomics, what is the right pill for your cancer. Colon cancer is not colon cancer is not colon cancer. Colon cancer is different in every human being, and everybody is different with their colon cancer. So we have to find the right treatment for your colon cancer and for your body. Next slide. Go on. So we can edit your genes now. We have genetic editing capacity. We can take your genes and we can cut them up, change things around, and give them back to you. And that's just a cartoon of how that happens. Next slide. We can change pieces, we can change long pieces, we can do what we want. It's called genetic engineering or editing. And now we've got a discipline called synthetic biology. Next slide. Where we can actually make new microorganisms. These are all made in a lab. Now that is almost encroaching on God's territory. But that's what we're doing. We're making living organisms. And we're moving into a very dangerous era, but we're also moving into a very exciting era. Next slide. And we might be able to use this technology to restore the damaged earth, because I'm not sure you're aware, but the earth is on the border, on the brink of extreme, possibly what they call the 6th extinction. We've poisoned the earth so badly that we need to do something dramatic and drastic to restore it. And there is a promise in genomic science that we might be able to do something about that. Next slide. These are the kind of environments that we have got to restore. This is not the Garden of Eden. Next slide. This is a common scene in south of Nigeria. How could human beings have done that to earth? It's unacceptable. Next slide. Now, all that synthetic biology, on that map over there, is all the centers around the world doing synthetic biology. But guess what? There is hardly any synthetic biology going on in Africa. That's a problem, because all those synthetic products are going to be tested in Africa. And if we don't understand it, we are going to be on the losing end. Next slide. There's now the concept, this is hot in the news. It's called the gene drive mosquitoes to eliminate the malaria carrying mosquitoes. They want to test these in Africa. They want to test these GMO mosquitoes who will be able to not carry the malaria parasites, and through this technology we might be able to eliminate malaria as we know it in Africa. It's a good idea, but it may come with some risks, and we need to understand what those risks are. You know about the famous sickle cell? Now we might be able to use genetic engineering to take that one code that is wrong, take it out and put the right code back in and give it back to the sickle cell patient and cure sickle cell. Most of you know how devastating sickle cell can be, and with simple genetics we might be able to correct that. HIV. Africa has the largest burden of HIV. We now know, and you heard about the story in the twins that were born a few months ago with a genetic manipulation that would stop them from catching HIV from their mother. And this gentleman here was the first patient that was cured through the use of a genetic concept from HIV. Nobody else has been cured from HIV. And so we have within our ability to cure HIV. The millions and millions of people living in Africa with HIV can be cured using genomics. Next slide. Now we're moving into transhumanism and augmentation. Next slide. Basically, that means we're going to be in an era where people are going to choose. I want vision that can see 5 kilometers. I want to be able to hear for 2 kilometers. I want a protected exoskeleton. I want larger computational analysis in my brain. And that's what's happening. It's a big debate, transhumanism. Next slide. And it is the marriage between genomics and computational quantum physics that is creating the opportunity for us to create human beings that are bionic. And that's not in the future, that is now. You see people are walking around with chips already buried in their skin and subject to all kinds of computational forces. So the convergence of man and machine is becoming a reality. And this comes with a lot of ethical debate. What is the right combination of man and machine? The convergence of man and machine. Can it be used to oppress other human beings? Can it be used to create insecure situations? Can it be used for aggression? Or can it be used for beneficiation? Next slide. Next slide. Now, lots of people want to live forever. So what is happening in certain centers is when you reach your peak, next slide, people are opting for cryotherapy. So we'll shut you down and we'll freeze you in these cabinets. And in about 50 years' time, when we have the cures for cancer, we have the cures for Alzheimer's, we have the cure for every known disease, we'll bring you back to life, and whatever disease you had, which we couldn't cure, we'll cure it, and you carry on living forever. This is not a joke. This is real. Next slide. Now, Africa, I'm almost through. Africa is focusing primarily on primary health. There's nothing wrong with that. But we have to be cognizant that the rest of the world is speeding ahead with precision medicine and augmentation. We can't be left behind. Otherwise, we're going to be taken captive again. Next slide. If you look at the global biotechnology rankings, All the colors in pink and red are where biotechnology is at a very advanced stage. And look at the map of Africa. Apart from South Africa, there is no country in Africa that has a serious biotechnology agenda. That is very scary and that is very worrying. Next slide. And those of you that watch athletics, my favorite race is the 4x100 relay because it's very aggressive. It's full of adrenaline and people are running at extreme pace. And you can see the looks on their faces in the Olympics. But if you drop the baton, by the time you pick up the baton and look up, the race is over. And that reminds me of where we are in Africa in terms of genomics and biotechnology. We seem to have dropped the baton. Can we pick up that baton and catch up? It depends. Next slide. The number of patents around the world are increasing exponentially. That's in China, that's globally. And the new Silk Road is bypassing Africa. It's going all around Africa and leaving Africa on its own. They come to Africa for resources, but we're not developing our biotechnology agenda. Some of you have heard of Elon Musk. He's an African. He's a white African, but he's an African. And he lives in South Africa. Elon Musk has developed the 100% electric vehicle. We are still driving cars that are booming black smoke into the atmosphere. He's trying, with his project, to fly to Mars. Not to the moon, to Mars. Next slide. We can't even get from Lagos to Ibadan without putting your life in danger. I do this trip every week. And when I get to Ibadan, I go like this. Because on the road, you will see accidents, you will see death, you will see the most outrageous things happening. What are we doing in Africa? Next slide. The next scary thing, this is where we are now. Population 1 billion. In 20, 30, 40 years' time, Africa's population is going to quadruple to 4 billion. We're going to be the most populous continent in the world. And almost every person on earth will be African or related to Africa. So we're going to take over the world. But how? If we're struggling with our 1 billion right now, what's going to happen when we're 4 billion? Do we have a plan? Do we have an expansion plan? Do we have a biotechnology plan? Do we have a plan to keep up? Next slide. The life expectancy graph, you've all seen this before. Income per person, life expectancy. That's the developed world, China, Europe, Japan, right up there. Living way to the 80s. Where is Nigeria? There. And the rest of Africa is here. And the rest of the world is up there. That just demonstrates our biotechnology agenda. Because it's biotechnology that keeps you alive. Next slide. These are the diseases that Africa has the largest burden of disease globally. Next slide. HIV ravaging us. Next slide. These are the kind of laboratories that we're accustomed to seeing in the rural environments. Next slide. This is not unusual. This is a typical primary health care center anywhere in Africa. Not even Nigeria, Africa. I don't want to be too hard on Nigeria. Africa. Next slide. This was how we responded to Ebola in Sierra Leone. Outdoors. Makeshift. What are we doing? Next slide. Next slide. So what is the strategy? We need a dramatic mindset shift in our political leaders across the continent. We need to drive a policy reform and enforce it by law. We need to empower academics. Our academics are moving like they're running away from a plague. They're leaving the continent. We're not looking after our academics. America is welcoming them because they're bright, they're intelligent, they're driving the American economy. We need a leapfrog mentality. We need to leapfrog into the future. We need to empower our youth. Majority of the people on the continent of Africa are young, but they've got nothing to do. They don't have electricity, they don't have security. The only thing they have is a cell phone. That is a leapfrog. When you want to buy your child a cell phone, you don't buy them because you're living in Africa. I'm going to buy you that brick. Do you remember what the brick is? That old-fashioned phone? No. Your child will look at it and say, what is this? How do you use this? You buy them, usually, one of the latest versions of iPhone or Android. That's a leapfrog. And they know how to use it. Our training curriculum must change. You can't keep teaching medicine in ancient textbooks. Medicine is genomic. We need energy and we need security. We don't have energy. I don't have electricity in my house. I don't know about you. There's nowhere I've been to in Nigeria where I have constant supply of electricity. It's either a generator is blowing, the light is coming up, it's going down, it's blowing my computer, it's doing all kinds of things. And there's huge potential in the private sector, but the government has to create an enabling environment for the private sector. If we're going to redefine medicine, we need scientists. We need what we call bioinformaticians. These are the people that are going to understand the unlocking of the genomics, all that huge data that comes out of genomic analysis. We don't have any bioinformaticians in Nigeria. How are you going to unlock your genomics? Dr. Jide Idris is here. He's looking for bioinformaticians. He can't find them for his projects. Without a bioinformatician, and I'm talking to the young people here today, if you want a career where they're going to snap you up like gold, and we will struggle to keep you in Africa if we train you as a bioinformatician, that's one of the professions to go into. Our pathologists need to become next generation pathologists. Next slide. So how do we get the genomic train to make a stop in Nigeria? I alluded to some of the issues that we need to do. It's not going to stop unless you create a platform for it to stop. And I'd like to applaud two people for trying to establish a stop for the genomic train. With the advent of the Ebola outbreak in Lagos, the Commissioner of Health has been able to set up a first-class biosecurity facility so that the next time we have an Ebola or Lassa or monkeypox or flu pandemic, we're able to manage it properly. And the whole world is being attracted to this place. So that is creating a train stop. The Director General of the Nigerian Institute of Medical Research, where I work, he's also trying to create a train stop so that we can attract the huge amount of knowledge that's going on internationally to make a stop in Nigeria, in Africa, to kickstart Africa's genomic agenda. Now I've come to the end of my presentation. In the person of Funmi Alakija, the little I knew of her, she showed me around her facility some years ago. And I've been back to that facility, and I am always in awe at the standard of that facility. It's no ordinary facility. What are the traits of this lady? She was a perfectionist. I think everybody knows that. She paid attention to detail. Now, these are all the attributes of genomic scientists. She was a visionary. She was dogmatic. Nothing would stop her. She was persevering. She was focused. She was oblivious to obstacles in her environment. And what she set up is an edifice that we can still see today. And that's why we're all here. If we had minds like Funmi Alakija in Nigeria, paving the way, putting pressure, advocating, then we have a chance to move forward and to narrow the gap between the developed world and the underdeveloped world. And thank you very much for your time.